OK，哦，麻烦声音关小一点。OK，好，这样好。OK，这样可以。Time for today's lecture. I know I said it many times, but allow me to say it again. I really appreciate your participation. It means a lot for me. Okay, now this week we will enter the third part of this course. And the topic of this part is about mathematical model of control systems. And in particular, we will study the behavior of control system in time domain, all right? Now, the first topic we want to talk about is about system models, okay? To design a control system, we need to perform system modeling first. Why? There are at least 4 reasons. The first reason is by performing system modeling, it is good for us to gain a better understanding of system behavior because it provides insight into how a system responds to different inputs and disturbances. Okay, this is very important because when you observe a person, how do you know its personality? You see how this person reacts to difficulties, to challenges. Same thing happened to control systems, all right? This understanding is fundamental for designing effective control strategies. If I don't understand my system, I probably won't be able to control the system, right? Pure and simple. Prediction and simulation. Models allow engineers to predict system behavior under various conditions without the need for physical testing. Because once you have a model, you can use techniques such as computer simulations to simulate the behavior of the system under different operating conditions. Okay? Without such a model, if you want to obtain similar information, you probably have to conduct experiments, perform so-called physical testings, which is time-consuming and which is also very expensive. Okay, so system modeling is therefore very helpful for helping us to overcome those problems. The third reason is about controller design. Many control design techniques rely directly on mathematical models of the system. That is, we have many different controller design methods. To use those methods, to implement those methods, the precondition is that we need to have a mathematical model for our systems. Otherwise, we are going to nowhere, okay? Those control methods will not be usable for us. Stability analysis. As we said in last week, stability is the #1 concern in conducting controller design, all right? If a control system is unstable, there is nothing left to talk about, okay? Because the system will definitely crash. Now, but with system models, models enable engineers to analyze system stability. For example, as we described last week, by ensuring that all the poles are located in the left half side of the X complex plane, a system is asymptotically stable, right? So the reason we can do that is that we have a system model which we call transfer functions, all right? And by examining the location of the poles of the transfer functions, we can identify, or we can at least investigate the stability of the system. Now, The modeling process typically can be divided into 4 phases. The first phase is assumption and hypothesis. We need to make some assumptions to simplify our problem. For example, we'll assume friction is negligible. For example, we will assume that many effects, which in reality are nonlinear. But we can also, sometimes we can reasonably assume under some operating conditions, a system can be considered to be linear, okay? Of course, these assumptions and hypotheses needed to be tested, okay? So once we make those assumptions, and typically based on some physical laws, we can perform mathematical formulations. That is, we can set up a set of sometimes a single differential equations to represent the system. As we said many times, the differential equation itself represents the system. The forcing function of the differential equation represents the output, and the solution of this differential equation represent the output. The forcing function represents the input, okay? So we need to solve the differential equation. Once we have the solution of the differential equations, what we have is prediction of the output variable of the control system. And then with those predictions, we can check model predictions with known facts. For example, my prediction results are my prediction results in good agreement with real experimental results? If they are, then probably my model is good enough. Otherwise, I probably had to go back to examine my assumptions and hypotheses, and if necessary, increase resolution of the model, which means I have to increase more details into the model so that my model can be more reliable and more accurate, right? So what is the mathematical model in this course? As we said many times, in this course, we considered nth order linear time invariant continuous size system, okay? And such a system can always be represented by this differential equation, okay? Remember that we said it many times. These coefficients are all constants. Now, none of them can be function of time. Okay, if all these equations are constant, then this is a time invariant system. The forcing function here represents the input. The solution of the differential equation is the output, all right? Now, let me give you some sample examples to illustrate the idea of system modeling. This is a very simple series circuit. Here, we have a voltage source, and then we have some 3 passive electric elements. One is resistor, the other is capacitor. This one is inductor, and I denotes current. V, of course, represent voltage, okay? We all know that the cross voltage of this resistor is V equal to IR, okay? And the voltage drop across the capacitor is 1 over C over Q, where Q is the charge. And here, the voltage drop across the inductor is L times the derivative of the current, okay? Now, based on the KVL law, we know that this voltage source should be equal to the voltage drops across these 3 elements. Therefore, we have this differential equation. The problem of such a representation is that we have two dependent variables. One is I, the other is Q, all right? And we know that I is actually the derivative of Q. That is, current is actually the derivative of charge. So we can rewrite this equation by using this equality. For example, the dt, that is the derivative of the current, cannot be rewritten as the double derivative of the charge. And we can apply the same technique to rewrite this term. So I now become R times the derivative of Q. All right? So what we have here is, of course, a second order differential equation. All right? And it's a linear time invariant system because all these three parameters are constants. All right? Now, if you are not happy with this representation, that is, if you think the dependent variable should not be charge, it should be the current. And then what you can do is replace this Q by the integral of the current, all right? And this differential equation cannot be written as this equality, all right? And the problem of this equation is that you have derivative and integral at the same time. So mathematically, it's more tedious to deal with such an equation. Note that this kind of equation, which involves derivative and integral at the same time, is referred to as integral differential equation, okay? But typically, we don't want to deal with this kind of differential equation. We prefer linear second order differential equation, all right? Because it is an ideal prototype for controller system design, all right? Now, what we have done is, for this series circuit, we set up a differential equations or common differential equations to represent the behavior or to characterize the dynamics of this electric system, all right? We can do the same, pretty much the same thing to mechanical system. What we have here is we call a spring mass damper system, all right? For example, a mechanical suspension system is made of, for each wheel, is made of such a spring mass damper device, all right? So to set out an equation of motion for this device, what we need to do is use the technique. The first thing we need to do is to draw a free body diagram, okay? What is a free body diagram? You learned that before, but let me review the idea of free body diagrams again here. A free body diagram is a simplified sketch of the object that shows all the external forces acting on it. So mass is the object. And what external forces we have here? We have three external forces. The number one external force is the force we apply to this mass. For example, ground reaction force applied to the tire can be chosen as F. Okay? Now, there are two other external forces. The first external force is the spring force. And we all know that from the law, Hooke's law, that spring force is proportional to the deformation of the spring. And the proportionality constant here is K, which is the stiffness or the spring constant of the spring, all right? Now, the final external force is damping force, come from the damper, okay? Now, this force is proportional to the velocity, okay? The spring force is proportional to the displacement of this object. By contrast, the damping force is proportional to the velocity of the mass. For example, let's imagine yourself standing quietly, standing still in the sea. Without any movement, you won't feel any resistance. But once you start to move, you feel resistance, okay, from the water. And the faster you want to move, the higher the resistance, okay? That's damping force, okay? So with such a free body diagram, and we can use Newton mechanics to set up equation of motion, okay, for this spring mass damper system. How do we do that? According to Newton mechanics, what we have here is summation F equal to ma. M, of course, is the mass. A is the acceleration, which can be rewritten as x double dot. And what are the forces? Of course, F minus bx dot minus kx. By rearranging the order of these terms, we can finally come up with this equation of motion. Again, it is a second order linear time inverse system. What we have here, similar to what we have here, okay? Physically, they represent different hardware, but mathematically, they are all represented by a second order linear differential equations, all right? So spring mass damper systems are actually very, very important in control because it is fundamental in control engineering because it is the simplest dynamic model that captures essential effects of inertia, stiffness, and damping, okay? The effect of inertia comes from the mass. Stiffness comes from the spring, and damping comes from the damper, okay? And as a result, making it a universal prototype for many real-world systems, okay? If you want to study a system, probably one of the best ideas is to model it as a second-order differential equations and to understand the physical meaning of how that system performs, how the parameters of that system correlate with the actual behavior of that system. You can think of that second order system as a spring mass damper system, and you can consider the behavior of that system in terms of inertia, stiffness, and damping, because these three terms all have very straightforward, easy to understand physical meanings. Okay, so a good thing about spring mass damper system is that a spring mass damper system is that it illustrates many key behaviors like such as stability, acceleration, and transient response while maintaining mathematical tractable for analysis and controller designs. Okay, the reason why we want to stay with such a system is that a spring mass damper system can be described by a second order differential equations. And in the course of engineering mathematics, we have already learned a bunch of mathematical techniques to tell us how to solve those equations, to teach us how to deal with those equations. So second order systems such as spring mass damper systems are mathematical tractable, okay? So it is relatively to study by maths, okay? And therefore, it serves as a bridge between theory and application, forming the basis for more advanced control concepts. That is, in the real world, there are many systems which are much more complicated than spring mass damper system. For example, a spring mass damper system, as we already know, is a second order system. You may have to deal with higher order systems, but even under that circumstances, second order systems still represent the basis for dealing with those advanced control systems. Now, here I want to introduce an idea called analogous systems. Now, this is a series circuit. This is the spring mass system we just talked about, and they can also all two of them can be represented by second order differential equations. So they are therefore analogous systems, because analogous systems refer to systems from different physical domains. For example, from electric domain or from mechanical domain. It can also come from thermal or fluid system. Although they come from different physical domain, but they exhibit mathematical similar behaviors. Okay, physics different, but in terms of mass, they are basically the same. If that is the case, we can call them analogous systems. This system can be modeled using equivalent mathematical equations, therefore allowing for the application of control techniques from one domain to the other. Okay, so for example, if you want to perform experimental studies for these two systems, conducting studies for this system is much more complex than performing experiment for such a simple circuit, right? Putting a series circuit together is, I wouldn't say a piece of cake. It is really not that difficult because all these elements are easily commercially available, okay? Connecting these elements together is also not a big deal, okay? And you can use simple devices, okay, to measure the current, to measure the voltage drops of this circuit, all right? But performing experiment for this system is much more complex because it involves mechanical elements, and you need to use probably expensive and sophisticated sensors to measure acceleration, to measure velocity, and to measure experiment displacements, all right? So it's not an easy job. But if they are if they are identical in the sense of mathematics, then let's say if you pick the right elements, then the differential equation of this model can be identical to the differential equation of this model. Then any experimental results obtained from this model can be applied to this system. Why? Because although they are physically different, they are mathematical equivalent, all right? That's the idea of analogous systems, okay? All right? So because they have equivalent mathematical equation, the concept of analogous system relies on the idea that different types of systems may have the same underlying dynamics. Therefore, the result from one system can be readily generalized to another system, as long as these two systems are analogous. Okay, let me give you another spring mass damper system. Okay, here we have a spring mass damper system we saw before, but now they are attached to the wall of a moving cart. Okay, so this, I assume it is a massless cart, so the mass of this cart can be ignored. Okay, now by drawing a free body diagram of this mass, and by applying Newton mechanics, I have these equalities. Okay, this represent ma. Okay, and this represents the damping force, which is proportional to the velocity. Okay, here the velocity is not the absolute velocity of this mass, but the relative velocity between this car and this mass, right? And similarly, the deformation of the spring constants is actually the difference between y and u. Therefore, the spring force is not minus ky, but minus k times the difference between y and u, all right? By rearranging terms of this equation, we can have this equality. And by taking Laplace transform of this differential equation, and at the same time assuming zero initial conditions, we can have these algebra equations, okay? I hope this conversion looks very natural to you, okay? It won't be something look totally strange to you, okay? All right, but remember that here, from here to here, we have to assume all the initial conditions are zero, okay? If that is true, then we have these algebra equations in the X domain, and then we can set out a transfer function for this model, okay? Let me tell you again that transfer function is defined as the Laplace transform of the output to the Laplace transform of the input, okay? From this equality, it can be easily shown that this transfer function, that is the ratio of y to u, is actually this ratio. That is the ratio of bx plus k to mx squared plus bx plus k. Now, since this is a second order system, therefore, the characteristic equation is a second order polynomial. Therefore, this system will have two poles because a second order polynomial always has two roots. Each root corresponds to a single pole. Okay? Now, here I want to review what we talked about before for the X domain system analysis. Remember that in this course, we're considering an causal LTI, ordinary differential equation. Okay, that is an LTI, linear time invariant system, which can be represented by this differential equation. Here, the input is no longer R, but another sample, X. I apologize for the inconsistency of the notations. Okay, because my materials come from different sources. And of course, different sources use different notations, okay? I will try to resolve those problems in the future, okay? But for the time being, please bear with me. Okay, now these are my initial conditions for the output. And Q, which is the characteristic polynomial, is defined as this. And P of X is defined as by this inequality, all right? We saw this before, okay? Now, what we need to do next is take the Laplace transform of this differential equation based on this equality of Laplace transform, all right? Which involve two parts. The first part is x to k times y of x. And the second part involves initial values of y, all right? So it can be shown that by using this equality, by taking this to transform this differential equation into X domain via Laplace transform, we will have this result. And solving for y will give us this equality, okay? This is what we call zero zero-state response, and this is what we call zero-input response. And h of x is, of course, transfer function, all right, because it represents the ratio of y to x, all right? And remember that the roots of p of x, that is the root of the numerator of the transfer function, is the zeros of the system. And similarly, the roots of the denominator of the transfer function are called the poles of the system, okay? Now, one thing is clear, that is the locations of the poles and zeros matters, okay? They are important parameters of the systems. So therefore, in the later part of this course, we will introduce you the impacts of the location of the poles and zeros on various aspects of system performances, all right? But here, let's just tell you how to identify the locations on the X complex plane. Let's say the transfer function is this. The system we are considering has such a transfer function. Apparently, it has two poles. One is located as -1. One is -2. And the zero apparently is located as this point of -3. Typically, we represent poles, but by such a cross sign, and we represent zeros by circles, all right? Poles, zero, all right? So this is a simple graph to help us understand the absolute and relative locations on pole and zeros. And we will see this kind of graphs in the future again and again and again. Now, in this slide, I want to re-emphasize the significance of transfer function. Remember that in the beginning of today's lecture, we told you that the goal of this part of the course is about mathematical model, okay? And transfer function actually is the mathematical model of the system, although it is presented in the X domain. So in analysis of linear time invariant system, the transfer function is our most powerful tool for understanding system dynamic behavior without having to solve underlying differential equation, okay? Because all we need to do is to deal with algebraic equations such as the characteristic equations. So we don't mess around with differential equations. We don't have to mess around with the differential equation anymore as long as we are in the S domain, okay, after the application of Laplace transform. So with transfer function, it allows us to determine stability by examining the location of its poles, right? Because in terms of asymptotic stability, what we need is all the poles are placed in the left half plane of the X complex plane, all right? So with the transfer function model, we can analyze frequency response of the system, okay? Now, it is too early to talk about frequency response, but right now, I just wanted you to have an idea that transfer function is vital. It is very good for frequency domain analysis, okay? Now, remember that transfer function actually is an algebra ratio of polynomials. Why? Because it is equal to px over qx. Px is a polynomial. Qx is also a polynomial. Therefore, transfer function is an algebra ratio of polynomials, all right? Now, based on that idea, the transfer function provides a common language for analyzing, designing, and interconnecting system through block diagrams. That is, in the later part of this course, we will interconnect many systems in different ways. And that is, we will build a block diagram to represent system, which is made of many subsystems. And each of those subsystems can be represented by its own transfer function, okay? And block diagram analysis is only possible when we have transfer function model for each of those subsystems, okay? So transfer function is the foundation concept that enable us to design controllers. That is why transfer function is very important. Now, in addition to transfer function, which is related to the zero-state response, we also had to deal with the impacts of the initial conditions. And remember that the output actually consists of two parts. The second part represents the contribution of the initial condition. And for this part, again, we see a ratio, okay? A ratio of I of x, which is also a polynomial to characteristic equation, okay? We already know what P of x is. We also know what Q of x is. Both of them are well defined. What is I of x? It can be shown that I of x actually come from here, the initial conditions. Now, and it can also be shown that I of x can actually be represented by this equality where phi of k is defined here, okay? Now, you can always determine phi of k for every k, all right? Because all these AIs, all these coefficients of AI are known, okay? They are given, right? They are given here, all right? So overall, we should be able to determine I of x without any difficulty, all right? So finally, we can have the total response in the x domain, all right? And it, as I said it again, and again, it consists of two parts. The first part is zero-state response, which is this part, okay? Now, we need to perform inverse Laplace transform in order to examine the zero-state response in the time domain, because it is in the time domain things are really happening, all right? So let's take it up in the inverse Laplace transform of the product of h and x, all right? Now, and what we will have is a convolution integral of h and x. X, of course, is the input. This h represents the impulse response of the system, okay? Because it is simply the inverse Laplace transform of the transfer function. And the zero input response, we can also take the inverse Laplace transform, okay? Now the total response is, of course, the sum of zero-state response and the zero input response. Now, the impulse response, as I just described, is the inverse of Laplace transform of the transfer function. And therefore, it is the inverse Laplace transform of the ratio of P of x to Q of x, okay? That's just a review of how we use Laplace transform methods to determine the response, total response, impulse response, zero-state response, zero input response of a linear time invariant system. Why do I want to review this concept? Because again, I want you to learn them by heart. I want you to remember the concept behind all those responses, because they are physically very important, all right? For example, in controller design, what we can deal with, the focus is always on this part, right? Because this part comes from the initial conditions, and our input cannot do anything about it, okay? We just have to accept them as the way they are, okay? There is no way to get around, all right? But what we can do is we can plan for the best input. And hopefully, by using a good control strategy, we can come out with a good zero-state response. And this part of the response, it can be shown that for a stable system or for an asymptotically stable system, this part will eventually disappear. It will converge. It will die out naturally. So in the end, that is in steady state, this will take total control because this will always go away as long as the system is asymptotically stable. All right. Now, let me introduce a term called DC gain, which has been often mentioned in the process of controller design. In control system, DC can refer to the steady state gain of the system where the input is a constant. All right. That is, let's say this is a linear time invariant system, okay, represented by a transfer function. Let's say the input is nothing but 1. That is, what we have here is a unit step input. Now, when time goes to infinity, let's say the output of the state, the steady state value of the output is A, okay? Then the DC gain of this system is A over 1, or simply A, because DC gain is defined as the steady state gain of a system when the input is a constant. And therefore, it tells you how much the output will settle to in response to a constant input after all transients has died out, all right? So mathematically, its formal definition is that for a linear time invariant system with transfer function h of x, which is equal to y of x to x of x, y again is the output, x again is the input. DC gain can be shown, it is actually h of 0, okay? And therefore, it is actually the ratio of y of 0 and x of 0. I will not be able to explain where does this equality come from, because to prove this equality is true, I need to use some frequency domain analysis methods, okay, which we are still unfamiliar with, okay? So we will delay the mathematical proof of this equality in the later part of this course. But for the time being, just remember the definition of DC gain and just have a very strong impression that you can actually determine the DC gain by setting x to 0 to the transfer function, all right? Now, here, let's start to study a real system from the sample system. That is, we will focus first on first order systems. Now, first order system, as you can imagine, can be represented by first order differential equation, all right? Similarly, systems such as spring mass dampers can be represented by second order differential equations and therefore are referred to as second order systems. Now, to illustrate the basic concept of first order system, let's consider Newton's law of cooling, okay? Now, what is Newton's law of cooling? Newton's law of cooling describe how an object's temperature change over time when it is exposed to a surrounding environment of different temperature, such as this case, okay? Let's say I have a cup of hot coffee with a temperature actually it is a cup of tea, okay, whose temperature is 6 degrees Celsius, and the surrounding temperature is about 25 degrees Celsius, okay? Now, from everybody know that if after a while, okay, when the time is long enough, the temperature of tea will eventually reach 25 degrees Celsius, okay? But how do I go from here to here? For example, how does the temperature profile look like as time progresses? Okay, we all know that initially it is 60, and eventually it is 25. But what is the shape of this profile? How fast is this profile? Okay. Now, what determines the shape and speed of that profile? Okay. Now, and Newton Cooling's laws tell us several things. The first thing is that the rate of heat loss of body is proportional to the temperature difference between the body and its surrounding. So the larger the temperature difference is, when I say temperature difference, I mean the difference between the temperature of the tea and the surrounding temperature. All right. The larger this difference is, the higher the rate of heat loss. Okay. This seems very natural. Okay. Now, however, we have to make two assumptions. Remember that before setting up a mathematical model for my physical systems, we have to make assumptions. Okay. The first assumption is the surrounding temperature remains constant. It is always 25 degrees. This might not be true, right? Because weather changes all the time, okay? Heat transfer is primarily through convection. There are two different types of heat transfer, three different types of heat transfers. Convection is only one of them. We also have conduction and radiations. They are also possible means for heat loss. But we just assume in this particular case, heat loss due to radiation and condition are negligible, all right? Which again, may not be true, okay? But generally, it is reasonable. Object has uniform internal temperature. When I say 25 degrees for the tea temperature, I mean the whole cup of tea has a constant temperature of 25 degrees Celsius, which again may not be true, okay? But these are my assumptions, okay? So to understand the limitations of my model, I first have to examine how correct my assumptions are. This is a very important step, okay? Now, with such assumptions, with the Newton law of cooling, we can now set a differential equation for this phenomenon of heat loss or the temperature variation of the tea, okay? Now, Newton's law of cooling tells us this has to be true. Where T, capital T here, small t, of course, is the time. Capital T represents the temperature of the object at time t. And in this case, is of course the temperature of the tea, all right? TA represents ambient temperature, which is what we call the temperature of the surrounding environment, ambient temperature. And we assume it is a constant. And K is the cooling coefficient, and it is always larger than there, all right? So heat loss, the rate of heat loss is a derivative of the temperature, okay? And this is, of course, the temperature difference between the tea and the surrounding, all right? So with this differential equations come from the Newton law of cooling. Here, let's define output as Y, okay? I want to set that first order control system. to model this phenomenon. So my output variable is chosen as the temperature of the tea, and the input is, of course, the surrounding temperature. Okay, let's take a 10 minutes break.谢谢。